So the final thing I just want to finish today on is a slightly left field idea that has got some traction over the years, which is to say that most of our inferences about the existence of dark matter come from our interpretation of the dynamics of galaxies. In other words, they come from an application of Newtonian mechanics to these galaxies here. And when you start looking at these things and you start thinking about having to come up with increasingly exotic particle physics and things like that in order to explain it, and especially when you then start not to find that particle physics, there is another alternative. And that is to say, what if Newtonian mechanics, or even what if general relativity, is in fact wrong? And this leads to the idea of something called modified Newtonian dynamics. Also sometimes known as MOND. And the idea of MOND, what MOND first notices, is it says, if you look at the accelerations that are actually being experienced by, distant stars far out in the galaxy, out in the halo, they're incredibly small. They're like 10 to the minus 10 meters per second squared. And that is not the sort of acceleration we're used to testing, right? We're used to living on a planet in which our acceleration is 10 meters per second squared. And therefore, doing even microgravity experiments in space where you try and cancel out the gravity, it's very hard to get accelerations that are that small. And therefore, it notes that we haven't actually tested properly Newtonian dynamics, Newtonian mechanics, in scenarios where the acceleration is very small. And so the idea of MOND is the following. It says, I'm going to replace f equals ma with the following. I'm going to replace f equals ma with f equals m times some function mu, which is a function of something called a over a naught, times a. And this function mu, it's not times a over a naught, mu is a function of a over a naught. What we know is that at high accelerations, mu equals 1. So f equals ma. But what it actually says is that what I have is a function which I don't know exactly what the form's going to look like. But if I plot here a over a naught versus mu here, then what it's going to be in the low acceleration regime is going to be linear, and then it's going to gradually plateau so that in the high acceleration regime it's going to be equal to 1. So this is just linear down here, so a mu is just a over a naught for low a and 1 for high a. So at high accelerations mu equals 1, at low accelerations mu equals a over a0. And a0 is something new. It's an acceleration constant. A bit like the gravitational constant, right? It's a new fundamental constant of nature. And then when you realise that, when you write that in, so at low accelerations, f equals m a over a naught a equals ma squared over a0. And why does that help me, particularly? Because it means the following. For low accelerations, out in the distant regions of of galaxies, I can write the following. I can write that the force is equal to gmm over r squared. It's the gravitational attraction between the 2 points. It's very low acceleration, very low force, is equal to ma squared over a0. For a circular orbit, I can write a is just v squared over r. And so I can write m v to the 4 over r squared a naught equals gmm over r squared. And you'll notice the appeal here that my r's now cancel. So v to the 4 is just gma0. It's a constant, or, for fixed m, or it varies as, the fourth root of the mass, if m is increasing with r. So if you make that adjustment, then you naturally get flat rotation curves. And in many ways, it's not a very appealing adjustment because you just have to throw Newtonian mechanics out the window. But in the other way, people who are proponents, who argue for modified Newtonian dynamics, will say, but actually, this might be more appealing than having to put all of these bells and whistles and extra bits inside the standard model. And the argument is that if you actually do this, you can get a very good fit to certain velocity rotation curves with MON, sometimes even better than with dark matter. And so there are people who argue quite strongly for this. What I would note is that there are a couple of crucial problems. So the first is that this was dissolved to solve this problem. It was designed to solve rotation curves of galaxies. So if you set out with the aim of creating a theory that explains something, you can almost always come up with a theory that does that. And so you might ask, how does it work in, say, galaxy clusters? And the answer is, unsurprisingly, not so well. But again, its proponents will say that maybe okay with neutrinos. Whoops, not quite sure what happened there. With neutrinos. So the point being that neutrinos here are hot dark matter. We know that they exist, at least in some numbers, so perhaps MOND plus a small amount of hot dark matter does work. However, the big problem comes, in a sense, with merging it with relativity. Because A naught is a number. I can't remember if I've written down what that is already. I haven't written down what that is. A naught is a number. It's equal to 1.2 times 10 to the minus 10 meters per second squared. It's an acceleration. And you ask yourself, well, relative to what? Where do I measure that A0? What's my frame? And the answer is that you need to have an absolute frame of reference to do this. And that's why it's called modified Newtonian dynamics. And most people are very uncomfortable, therefore, given the spectacular success of relativity, to go back to some absolute frame. And people have attempted to address this as something called TeVeS, which stands for tensor vector scalar gravity. And that's every bit as complicated as it sounds. And I think the problem here is that whereas relativity is very elegant, these other theories become very complicated. And then what's the beauty of Mond, the idea that you take this very simple adjustment to Newton's laws that we have here, and it explains things, is really lost when you have to start coming up with something very complex. There is some appeal in making essentially gravitational forces weaker at large distances, which that it also has something to do with dark energy, potentially. If you change how gravity works, then perhaps you can also simultaneously explain dark energy. But overall, most people, both astronomers and particle physicists, would probably bet that dark matter is a solution, not changing your fundamental physics. But, that being said, we still don't know what dark matter is, and that's an open question really for your generation of researchers.